All right, make sure you have a calculator for today. Anybody need one? You're welcome. All right, so last night I asked you to view the video assignment related to these optimization type problems. And the first one that you should have viewed was kind of similar to the volume or box example we did yesterday, just with different dimensions. And it seems like from the responses that, just like usual, we're feeling okay, kind of confident, we just want more practice. That was weird. But I did have quite a few people mention how they were a little iffy on when we need a secondary equation and when we don't. And I can understand that because the volume example or box that we did yesterday didn't really have that component to it, but we will see some examples of that today. So more practice today, more practice tomorrow, we'll be good to go. All right, so on 321, a manufacturer wants to design an open box, so very similar to what we did yesterday, having a square base and a surface area of 108 square inches. What dimensions will produce a box with maximum volume, and what is that volume amount? Okay, so very similar to yesterday, just instead of knowing the dimensions of the box, or the dimensions of the paper, we know the surface area that this box should have. So it's a different piece of information. If we roll through these 5 different thought processes, or these 5 different methods, okay, let's kind of think about how we can approach this problem. So I believe number 1 from yesterday was what is being optimized. Can we figure out what we're trying to find the most or the least of? Do they say it specifically, or do we have to kind of infer it through something different or through something else? Volume, okay. So if we're trying to maximize volume, we're eventually going to have to write a volume equation. So this is going to be our primary. Okay, the main equation that we use. Yes, go ahead. Okay. What also might be what also might be good for us to do is to draw a picture of this scenario. So we have an open box. I know we're not Picasso's, I'm definitely not, but try to draw really? You had to draw boxes in that class?
Oh, we drew so many cubes, you wouldn't even understand.
Why?
It was just something we did,
Because we were bored, or you had to?
No, we definitely didn't.
Literally no reason.
Whatsoever.
Here we go. All right, so open box. There's no lid. The surface area is 108 square inches. Maybe we'll bring that into play in a little bit. How do we want to find the volume of this box? How did you find the volume of your box yesterday? Length times width times height. Okay, so it might be beneficial for us to label what those are in this picture. And it says we have a square base. So this base down here, if this distance is x, then this distance is also x. What can we label the height of the box as? H, y, okay, different variable, doesn't matter. We can't label it x though, because then we would be assuming it's the same length, and it might not be. Okay, we just know that the base is a square. All right, so for volume, if we do length times width times height, we'd have length of x, width of x. So if we multiply those together, it'd be x squared, and then times the height we'll have as h. Okay, so this is our main equation for this example. We're eventually going to have to take the derivative of this, set it equal to 0, find the critical points, test them, all that jazz. Now the issue is, with this equation, notice how we have 2 variables in here, an x and an h. and we only want one variable there to help us take the derivative of it. So somehow we need a secondary equation to either turn an x into an h or an h into an x. We're going to do a little substitution. So where do you think this secondary equation can come from? It's probably surface area, right? Because they told us that little fun fact, but we haven't really used it yet. So let's see if we can write an equation for the surface area of this box. So surface area is all the individual areas just added up. So if we do the area of the base, because it's a square, that'd be x times x. And then we have these four sides to the box. So the area of one side would be x times h. And if you're going to add 4 of those up, we'd have 4. Are we doing okay so far? Yeah?
Is the box open at the top?
Yep. Open box. All right. Now they told us the surface area had to be 108, so we can go ahead and fill that in. Now looking at our surface area equation, can we think about which variable would be easy to solve for, get all by itself? That way we can do some substitution into our volume equation. Probably h, right? Because there's only one of them there. So if we get h all by itself, we'd have to subtract the x squared and then divide the 4x. All right, so if this is h, we're going to substitute it in to our primary or main equation. Okay, now we're eventually going to have to take the derivative of this, and right now I think we could, but it would be highly involved because we have what looks like to be a product rule and a quotient rule. So maybe can we clean it up first so that we might not have to use so many shortcuts? Can you notice anything that we might be able to do? You're multiplied in? Okay, so 108x squared minus x to the 4th over 4x. So that kind of got rid of the product rule. Now it's solely quotient. You want to go through quotient rule? You want to simplify it more? Yeah. Up to you. How can we keep going? Yep, okay, so if we pull 1x out at the top, that can cancel out with 1x on the bottom. So we'd have 108x minus x to the 3rd, and all that's over 4. With the way it looks right now, it's still a quotient rule. Can we keep rewriting it, or do you want to go through quotient? Yeah?
You divide the 4 instead.
Yep. Yep, we're going to divide both pieces by 4. So 108 divided by 4 is 27. And then the other term would be 1/4 x to the 3rd. So I'm not saying you have to do this. Okay, I'm just saying if you simplify it as far as you can, it's just going to make the derivative process easier for you to go through. So now let's take the derivative. How do you want to write the derivative of volume? We can do v prime. You can write dv over dx, because that's our independent variable. Doesn't matter. Maybe I'll just do v prime. All right, so derivative of the right-hand side, we'll have 27 minus 3/4 x squared. Okay, so if our goal is to maximize volume, notice how that's the equation we want to take the derivative of, because if volume has a max, that means it has a slope of 0 at some point. So that's what we're trying to find. Let's set the derivative equal to 0 and solve for when this maximum might happen. I have so many arrows. Okay. Subtract the 27. And then divide over -3/4. 36. Okay. And then square root both sides. Technically plus or minus 6, right? So we have, hold on, we have 2 critical points. All right. Should we check both? No, why not? Right, this x distance can't be negative. So really, we're just going to check 6. Okay. So if it's a critical point, it's a potential max or min. We need to confirm it with a sign chart to actually prove if it is or not. So when it comes to setting up your sign chart, we can kind of think about what the bounds should be. I mean, the lowest this x distance could be is 0. But in terms of the highest, I'm not really sure what that is. I know we're restricted by surface area, but I don't really feel like calculating what that highest value is. It's not really necessary either, because we just basically got to pick a point before 6 and after 6. And we're going to plug that into the derivative. So what do we feel in between 0 and 6? 1. Okay, so let's plug it into our derivative. We'll have 27 minus 3/4. Positive. Bigger than 6? Probably 7. 7 squared, 49. 3/4 of that, more than 27. So 27 minus something bigger than 27 is negative. Okay. So based off of our sign chart, we've confirmed that we have a max at 6. So we'll go ahead and say volume is maximized when x equals 6 because derivative changes positive to negative. Are we done? No, we'd like to be, but unfortunately not. It says, what dimensions will produce the maximum volume? And then they also want the actual volume amount. So how can we figure out those pieces? Well, we had 2. The which one?
The age equation, because we have x.
Right here. All right, let's use our secondary one over here. So we know what x is, which means we should be able to figure out h. So if we plug in 6, this will be 36. 108 minus 36 divided by 24. 3. All right, so we'll have 6. So the dimensions of the box would be 6 by 6 by 3. Okay, length by width by height. Inches. I think that's our unit, right? Inches. And then our volume, if we do length times width times height, so 6 times 6 times 3. 108. So it looks like the surface area and the volume are the same amount. How are we doing? Decent? Okay, so the calculator really isn't going to be as necessary, at least for computation numbers. We don't really need it to help us graph anything. I guess you could. I mean, you could graph volume, find the max. That would be your critical point. But we can definitely do that by hand. Okay, solving with some algebra. All right, so the video assignment covered all of them on 322. We're going to skip that. We're going to jump to 323. All right, a solid is formed by adjoining 2 hemispheres to the ends of a right circular cylinder. Wow. The total volume of the solid is 12 cubic centimeters. Find the radius of the cylinder that produces a minimum surface area. So what should our primary equation represent? What's our main equation going to be? What are we trying to maximize? Yeah? I guess minimize, okay, or optimize in this case, so surface area. So we got to figure out what equation would represent the surface area of this shape. Now, if we draw it, a solid is formed by adjoining two hemispheres to the ends of a right circular cylinder. So a circular cylinder is basically a can or a tube. And we have hemispheres on the top and the bottom. So basically half a basketball on top and half a basketball on the bottom. I don't know, that kind of reminds me, if you ever been to the bank where you go through the drive-thru and they have those tubes that shoot up. It kind of looks like that. All right, so somehow we got to figure out a surface area equation for this shape. And if we think about it, this shape, this total shape is comprised of kind of miniature or different shapes just combined together. So notice how the top part and the bottom part is a sphere. And then the middle part is a cylinder. All right, these might be a little bit tricky. When we did related rates and we went through a whole bunch of different geometric formulas, I understand we might not know those. This is definitely a type of question where I would give you the formulas to help you with this. But the surface area of a sphere is 4 pi r squared. Can we think about what the surface area of the cylinder would be? Like if you were to paint the outside of it, how we could figure out that amount? Okay, so basically a cylinder is a flat piece of paper, and if you make a circle out of it, there's your cylinder. So the surface area all around this is just the area of a rectangle, right? Okay. So if we can figure this out, the area of a rectangle formed into a sphere, we would need this distance, so that's your height. And then we basically need this distance, but if you turn it into a sphere, that distance is now the circumference of a circle, which is 2 pi r. Okay. And to figure out the area, we would need this distance times this one. So h times 2 pi r. Does that seem about right? Okay. So let's put those together. So we have a whole sphere on top and bottom. And we're going to add the surface area of the cylinder, 2 pi r h. Now, since this is our primary or our main equation, we know we're going to have to take the derivative, set equal to 0, find critical points, sign chart, that whole jazz. But notice how we have two variables over here. We only want one. That way we can actually solve for a critical point. So there has to be some secondary equation we can figure out to help us replace an r with an h or an h with an r. So is there some other information given to us that can help us form a secondary equation? Volume. Okay, total volume was given. Okay, so for volume, we're going to need the volume of a sphere and volume of a cylinder. Again, these are a little tricky just to know off by heart. So volume of a sphere, 4/3 pi r cubed. Can we think about the volume of a cylinder? You're close with that. It,
Like the inverse derivative of the surface area.
the inverse derivative, antiderivative.
Yeah.
Okay, we're going to talk about that in the next unit. 2 pi r squared plus 2 pi r h. Okay. Actually, no. Nope, I copied that down wrong. Pi r squared h. Yep. I'm looking at the wrong spot on my paper. Okay, so for the volume of a cylinder, you're basically taking the area of a circle, that's the pi r squared, and then you multiply it by the height. Okay, so volume, we'd have to add those together because we have the volume of a whole sphere plus the volume of a cylinder. All right, and they told us total volume was 12. So is there an easy variable in here that we can solve for and substitute it into our primary equation? H, right? That's the only one. So to get H by itself, we'd have to subtract over 4/3 pi r cubed and then divide by pi r squared. So that craziness, we're going to substitute it in. All right, so technically we could take the derivative from here because we only have one variable now, but it would be very complicated because we have a lot of different rules or shortcuts going on. Can we clean it up? You see it, Anush? Yeah?
2 pi r and pi r squared.
Yep.
You can cancel out a pi r.
Okay, so pi's go away, and then this 1r would cancel out with one of the r's on the bottom. Okay, so what looks like we're left with, we can distribute in a 2. So this would be 24, and then minus 8/3 pi r cubed, and that's all over r. Okay, we could find the derivative from here, or do you want to try to keep simplifying it? Can we do something similar to the last one? Since we have one denominator or one term on the bottom, can we divide individually? Okay, so if we did 24 divided by r, you could write that as a fraction, or you can bring the r up and make it a negative power. So it'd be r to the negative first. And then for the next division, notice how a set of r's would cancel. So we'll have 8/3 pi r squared. You want to keep simplifying or derivative time? We could, okay. If you want to keep simplifying though, we do have like terms here. They both have a pi, they both have an r squared. Let's see, we can change this into 12 over 3, so they have a common denominator. And then 12 minus 8 would be 4. So 4/3 pi r squared plus 24 r to the negative first. That's probably as good as we're going to get it. All right, so derivative, we'll do surface area prime. And then derivative will have 8/3 pi r minus 24 r to the negative second. All right, let's set it equal to 0. And I'm going to go ahead, since I'm done taking the derivative, I'm going to make this negative power on the r positive again by moving it to the bottom. All right, where can we go from there to solve for r? There's a few different things you could do. We could, okay? We could graph it, find an x-intercept, that would help. Can we do it by hand? Let's see, you're technically subtracting two fractions together, so we could go the common denominator route. Technically, we could add this fraction over. Maybe we'll do that. Now this 8/3 pi r, you can turn that into a fraction by just moving the 3 over everything. What can you do if you have two fractions equal to each other? Cross multiply. All right, 24 times 3, 72. Right side would be 8 pi r cubed. I think we can solve for r from there. 72 divided by 8. 9. Divide the pi over. 9 over pi. Get rid of a cube. Cube root. All right, so there's actually our exact answer. We're going to turn this into a decimal just to help us out. So 9 divided by pi to the 1/3 power for the cube root. 1.42025. Units are centimeters. Okay, so here's a critical point. We need to confirm it. So in terms of our radius, the smallest value could be 0. Technically, we wouldn't have a shape then, but the smallest it could be is 0. We'll go to our critical point, and then critical point to something. Okay, we're restricted for our volume value, but I don't really feel like figuring out what the highest radius could be in that case. All right, so for our sign chart, what number are we feeling between 0 and 1.42025? 1. Okay, so where's our derivative? Here's our derivative. Let's plug in 1. 8/3 pi minus 24. That's negative. And then anything bigger than 1.4, probably 2. 8/3 pi times 2 minus 24 over 4. Probably positive, right? You can confirm on your calculator, type it in. So confirmed minimum. So we'll say surface area is minimized at r equals 1.420. If we go to 4 decimal places, chop it 2, round to 3, up to you. Because surface area derivative changes negative to positive. Are we done? Did we answer the question? Yeah, it says find the radius, which we did. So unlike the previous one, it looks like we're good to go. Right? We're starting to get the gist. We see the pattern. It's involved. Okay, at least these two are involved. The ones we do tomorrow might be a little less. But it's still kind of a thorough thought process or fluid thought process. What's being optimized? Draw a picture. Do we need another equation to help us out? take a derivative, equals 0, critical point, sign chart, justification. Okay? It's kind of the same deal for all of them. All right, but we'll check out the rest tomorrow.